Okay, so we're going to talk about the relationship between the cell potential, that E naught, which we call the cell potential, and the delta G, which we studied back in chapter 19, which was the free energy. So, what we know is that if delta E is positive, we can consider our reaction in our cell to be spontaneous. And then we also know that from chapter 19 that a reaction, and this is also a reaction, whatever's going on in the cell, that we know that a delta G that's negative is also indicative of a spontaneous reaction. So, what's the relationship between the two? Well, this is it. It's delta G is equal to negative NFE, where N is the number of moles of electrons that pass through the cell. So in the example where we showed the transfer of electrons from one electrode to the other in the voltaic cell, there were 2 moles of electrons. In one of those longer ones that I did, there were, something like, how many moles of electrons were in this one? It was 6 moles of electrons in this type of redox reaction. So that's how you would identify the number of moles for N in this. And F is a constant. It's called the Faraday constant. The units that we would use would be joule per volt mole. And E is your cell potential. So you can calculate your delta G or your E at standard conditions, and that's what that naught symbol means. G naught is free energy at standard conditions. E naught is cell potential at standard conditions, which just means that they come from table values. So we know that delta G can be related to the equilibrium constant, and if delta G can be related to the equilibrium constant, then E naught should also be related to the equilibrium constant. So we know that delta G naught is equal to negative RT, natural logarithm of K. And when we say K, we're talking about the equilibrium constant that we studied in chapter 15. And the reason there's an equilibrium constant is because we're talking about the values of the ions that are in solution in the this portion of the voltaic cell. So those ions in solution are also going to affect the free energy due to this relationship. So the equation for this relationship, delta G equals negative RT natural logarithm of K, and K is just the way you would normally calculate a K constant, but typically for these examples, it would be given. And so since this relationship is true, we can also say that this relationship is true because of this. So we can say that negative NFE under standard conditions is equal to negative RT natural logarithm of K. And R is the value 8.31. Okay, so 8.31 joule per mole Kelvin. And so to calculate the E naught, the standard cell potential, I can say that it's equal to algebraic manipulation, RT, natural logarithm of K, over NF, where N is the moles and F is the Faraday constant. So that shows me the relationship between cell potential and the value of the equilibrium constant for the ions in the solutions of the voltaic cell. So then we'll go to 7, and there's a nice example here. Slide 7, page 5. So in this example, you'll find on page 870 in your textbook, and this is the equation that's given, and the questions are, what is the E naught, which is the cell potential? What's the delta G naught, which is the standard free energy? And what is the equilibrium constant? And of course, the equilibrium constant would only involve this, and this, because in equilibrium, you don't include your solids or your liquid. But all we want to do is to calculate that K constant using the equation. So I would look at what is the cell potential? Well, the first thing I would do is I would look for the redox reaction, and I would get these values off of the table in the textbook. And I know that the E red for this reaction is positive 1.23. And then if I went to the table to look for the other reaction, it would be going in this direction, and the E red would be positive 0.80. But I know that the one with the higher value is the one that's going to undergo reduction. The other one will undergo oxidation. So I take this equation and its value, and I flip the equation around to show it as oxidation, and I change the sign. So then I know that the standard cell potential is positive 1.23 plus a negative 0.8, and I get a standard cell potential of 0.43 volts. Okay, so then the next part of the calculation, it asks me to find the delta G. So delta G is equal to negative NFE. So I can see that there are 4 moles of electrons that are transferred in this cell. And so I take the 4, multiply by the Faraday's constant, and then I multiply by the volts that I just calculated here. And you can see that all of your units cancel. So now my delta G for this reaction is going to be negative 1.7 times 10 to the 5th joule per mole, or negative 170 kilojoule per mole. So what do I know? I've got a negative value. I'm indicating that this is a spontaneous reaction, also confirmed by the fact that this is a positive 0.43 volts. Okay, so then the next part of the question is to calculate the equilibrium constant. So I'm just going to use this equation. Delta G is equal to negative RT times the natural logarithm of K. So I plug in my value, but I want it to be in joules. So I'm going to stick with this because this is joule per mole K. I think up here I said it was joule per mole. And I should have said, I think it was on the last slide, I said it was joule per mole, but it's joule per mole K. If I didn't say that, correct myself. All right, so the temperature, 298, sorry. The temperature given in the problem was 25 degrees Celsius. And then what's the natural logarithm of K? So I do a little bit of algebra. I get the natural logarithm of K is 69. I take the inverse natural logarithm of 69. I get 9 times 10 to the 29th. So that tells me what the K, the equilibrium constant for this reaction, would be. And then part B of the question just says something about what if you took the equation above and you divided everything through by 2. So I had this equation here and I divided everything through by 2. And so if that's the case, then I want to show you how things change in the problem. So the number of moles that pass through, the number of moles of electrons that pass through the cell would be divided by 2. Now this is important. The E naught does not change. It does not change based on coefficients. It's always the same value. So then if you plug those values in to your equations, what's going to happen is that because your moles are cut in half up here in this equation, then your delta G gets cut in half. And then when you plug into this equation here, your K value comes out to, I did it out, I didn't get 4, I got 3.5 times 10 to the 14th. That does not get cut in half. You have to figure that out by calculation. I'm going to stop there.